Hey, you guys. I realize that with testing on Wednesday, I won't actually see you in class, but we can't really skip a day. So we're going to do just a little bit of an intro into the fundamental theorem. This will be the kind of the mechanics of it, the algebra. And then when I see you again on Friday, and then next week, we'll talk more about the application and the meaning and everything implied. So this is 4.4 in your notes, and we're just going to do one page of notes here. It says the fundamental theorem of calculus states that differentiation and integration are inverse operations. Okay, the same way as addition and subtraction are inverse operations, or multiplication and division are inverse operations. The idea is that they undo each other. If I have a derivative and I want to go back to the original, I can undo the derivative by integrating. So think about it this way. Remember, differentiation represents the slope of the tangent line, right? Well, the idea of slope back in algebra days was, remember, slope is the change in y over the change in x. But integration, the other day we said it represents the area under a curve. And if you think about it, when we were estimating area by doing rectangles, right, I know that the area of a rectangle is what, base times height. But on our curves, you know, when we had a curve and we talked about the base of the rectangle, wasn't that the change in x? And if we talked about the height of a rectangle, you know, from here to here, wouldn't that be the change in y? So look right here, you can kind of tell that where slope represents, in essence, a division, area, in essence, would be multiplication. And that's just kind of a real basic way to think about that they are inverse operations. So here's the way the mechanics of fundamental theorem actually works. Now, first of all, I'm going to write kind of over here to the side the way we think of it. We would say that if I want to integrate a derivative, right, and let's say I have boundaries from a to b, we know that when you integrate the derivative, it takes you back to the original, right? And then the way the boundaries work is we say, hey, we're going to evaluate this from a to b, and this is just kind of a notation. So that means it's going to be the original function at b minus the original function at a. So that's the way we tend to think of the fundamental theorem of calculus. The way you see it in the textbook, instead of saying that you're going to integrate the derivative, they say, hey, if you integrate f, again, it doesn't matter if we call it f or f prime, this is still a derivative of something, right? And so this is saying we're going to let the original of that one be called capital F. So if you integrate little f, it takes you backwards to its original, which is capital F. And then we would evaluate that from a to b, which means you would plug in b and then plug in a. So I don't want you to think of these as separate formulas. It's just that I think that it's a little bit more clear for us to kind of think of it this way than it is to think about it as capital F, because you tend to forget that this function is a derivative of something no matter what you call it. Okay, so how does that work as far as doing the math? Well, straightforward. Forget the 1 and the 9. Can we integrate this? Now, I think what I'll do is I'll do it without having to do use substitution. So I'm going to think of this as the square root of 2, and if it's over the square root of x, wouldn't that be the same as saying you're going to multiply by x to the negative 1/2? And if I think about it that way, then I don't have to do use substitution. So I'm going to integrate, and I'm going to say, well, square root of 2 is just a constant, so I'll leave it alone. If I integrate this x to the negative 1/2, it's going to become x to the positive 1/2. And then instead of saying over 1/2, I'm going to say times 2. And then I need to evaluate that whole thing from 1 to 9. So that means I'm going to plug in 9 first. So out here in front, I have 2 square root of 2. And then if I plug in a 9, right, 9 to the 1/2, let's see, 9 to the 1/2, doesn't that just mean square root of 9? So that's 3 minus, now I'm going to plug in the 1, so that's going to be 2 square root of 2, and if I have 1 to the 1/2, that's just 1, and of course you don't need to write that, I just wanted you to see that I actually plugged it in. So basically what I have here is 6 square root of 2 minus 2 square root of 2 equals 4 square root of 2. So there you go. Okay, so that's the mechanics behind it. So take a look at example 2. If I'm going to evaluate this, first of all, I'm going to integrate the cosine. Let's see, that takes me back to sine. So I need to think about it. The derivative of sine is positive cosine, so that's going to stay positive. And then I would evaluate this from 0 to pi, which means sine of pi minus sine of 0. And in this case, the sine of pi is 0. So 0 minus 0 equals 0. So just a little, I mean, I'm done with this problem, right? It's going to equal 0, but just a little something to think about. Remember we said how integration represents area, so can the area be 0? Well, if you think about the graph of the cosine function, doesn't it do something like this? And if I look at it from 0 to pi, here's 0, here's pi, wouldn't it have the same amount above the x-axis as it has below? And so that's why the quote, the positive and negative space kind of cancels itself out, and the integral actually equals 0. Okay, so let's look at the last one here. How do I integrate absolute value? Well, I mentioned the other day, just like derivatives, we will never actually integrate an absolute value. So what we have to do is we have to think about the graph. Okay, so if I think about the graph of x squared minus 1, right, isn't that just a parabola that's moved down 1 unit? So I've got this parabola. And what does absolute value mean? Well, it means the part that was below, right, the part that was below becomes, flips up and becomes positive. So in other words, this part stays the same, right? The part that was positive stays the same, but this part that was below is going to flip up. So that would actually be the graph of the absolute value of x squared minus 1. And if I want to evaluate this from -2, say right here, to +2, right here, that means I want all of the area from here all the way underneath here and then over to here. So I've got to figure out how to find this area. Well, I hope you would agree that these outside pieces, because of the symmetry, are going to be the same, right? So, and this curve right here was actually just the basic x squared minus 1 parabola, right? So if I want to find this area, I would be integrating, well, what is this x-intercept? Well, wouldn't that parabola hit at 1 and -1? So it would be from +1, and remember we're going to 2, and then I'm actually integrating that basic parabola, so x squared minus 1. So I think that this integral would give me this pink space over here on the right, and because of symmetry, that would equal this pink space over here on the left, so I'm just going to double that. So that should take care of the pink part. I can do that in a minute. And then I want to add to that this area here, right? Well, I think you would agree that's going to be the integral from -1 to 1. So now the question is, well, what's the equation of this? Well, that's not the basic parabola. That was the parabola after it was flipped up. Well, think about it. If you flip something across the x-axis, doesn't that make it negative? So essentially, wouldn't that be the graph of -x squared plus 1? So if I integrate this -x squared plus 1, that's going to give me that green area. So this is what I'm going to have to do in order to actually come up with the total area. So just to kind of finish that, let's see, over here I would have x cubed over 3 minus x. I'll evaluate that from 1 to 2, and then I'll multiply that whole thing by 2. So I'm going to have 2 If I plug in the 2, it's going to be, what, 8/3 minus 2. And then now minus, if I plug in the 1, that's going to be 1/3 minus 1. But remember, I'm subtracting this whole thing, right? So that, I can do that math. That'll give me the pink part. And then just to kind of set it up for you, over here, it's going to be negative x cubed over 3 plus x. And I'll evaluate that from -1 to 1. So if I plug in a 1, it's going to be -1/3 plus 1. And minus, if I plug in a -1, that's going to become a positive 1/3 minus 1. And again, I'll let you do the math. I don't even care if you do the math, but if I put all that together, I could find that total area. Okay, so just something to keep in mind. The homework from this particular day, it was just practicing this concept of doing the integration and plugging in the numbers. It's on your calendar, but I'll put it down. So you're going to do from section 4.4, I think it's page 293. You're going to do number 7 through 33, every other odd. And then from section 4.5, you're going to do page 307, number 75 through 85. And on that section, it's the odds. Okay, so we just need to kind of get the mechanics down of this fundamental theorem. So good luck with that. Make sure you check your work, and then we'll go over that on Friday.